13 years. That's how long the Kepler Space Telescope stared at a single patch of sky, roughly 0.25% of the total sky, and counted planets. It found 2,662 confirmed ones. Scale that up across the whole sky, and we're looking at somewhere between 100 billion and 400 billion planets in our galaxy alone. And our galaxy is one of roughly 2 trillion galaxies in the observable universe. The numbers are so large, they stop meaning anything. So here's the thing that should bother you. We've been broadcasting radio signals into space since 1895. We've had telescopes scanning for artificial signals since Frank Drake pointed a radio dish at 2 nearby stars in 1960. We've sent physical probes. Voyager 1 has now crossed into interstellar space. And in all of that time, across all of that sky, with all of that listening, nothing. Not a blip, not a pattern, not a single signal that held up under scrutiny. The universe is 13.8 billion years old. It had billions of years to produce life before Earth even existed. Some stars in our galaxy are 10 billion years older than our Sun. If even one civilization had started just 1 million years before us, which on cosmic timescales is barely a rounding error, they could have colonized every star system in the Milky Way, using technology not much more advanced than what we're building right now. And yet, nothing. This is called the Fermi paradox, named after physicist Enrico Fermi, who, during a lunch conversation in 1950, asked the question that has haunted astronomers ever since. Where is everybody? That question sounds simple. It's not. Because the deeper you go into it, the more it stops feeling like an astronomy question and starts feeling like a question about whether we should exist at all. There are only a handful of possible answers. Each one is stranger than the last. And one of them, the one scientists call the rare earth hypothesis, suggests something genuinely disturbing. That life as complex as ours might require such a specific, improbable, almost absurd combination of conditions that in a universe of 2 trillion galaxies, we might be it. Not special in the way people say at graduation speeches. Special in the way a winning lottery ticket is special. Not because it deserved to win, but because someone has to win, and the odds against it were enormous. This video is about what it would actually take for that to be true. The geology, the chemistry, the orbital mechanics, the lucky accidents of our solar system's formation. What conditions would have to be in place? Which ones we have? And which ones, when you look at them carefully, are genuinely hard to explain. The optimistic view, the default assumption in most science journalism, goes something like this. The universe is so big that even if the probability of life arising is tiny, it's going to happen billions of times over just by sheer volume. It's a comforting argument. It also has a flaw. Probability doesn't scale the way people intuitively think it does. If the probability of something happening is 1 in 10 to the power of 40, multiplying it by 10 billion planets doesn't make it inevitable. It makes it still essentially impossible. The question isn't whether the universe is big. The question is how improbable life actually is, and that number we genuinely don't know. We have exactly one data point. Earth. That's it. One confirmed case of life in the observable universe. Statistically, you cannot construct a meaningful distribution from one data point. You can't say life is common and you can't say it's rare. You just don't know. But here's what we do know. We know what it took to get here. We know the geological history of this planet. We know the chemistry that had to happen. We know the position of Earth in the solar system, the role of Jupiter, the timing of the moon's formation, the specific properties of plate tectonics. And when you go through that list, one item at a time, you start to notice something uncomfortable. These aren't simple requirements. Each one is the kind of condition that if you were setting up a system from scratch, you would not naturally expect to land on. Let's go through them. The habitable zone, sometimes called the Goldilocks zone, is the range of orbital distances from a star where liquid water can exist on a planet's surface. Not too hot, not too cold, just right. It's the first filter every potentially habitable planet has to pass. And it sounds simple enough. Here's the problem. The habitable zone is calculated assuming a planet has an Earth-like atmosphere. Change the atmosphere, thicken it, thin it, alter its composition, and the effective habitable zone shifts dramatically. Venus is technically within or near the inner edge of our Sun's habitable zone, depending on the model. Venus has surface temperatures of 465 degrees Celsius. The lead on its surface is molten. It's not a zone problem. It's an atmosphere problem. Mars is within the outer edge. Mars is currently a frozen desert with atmospheric pressure so low that liquid water can't exist on its surface in stable form. Not a zone problem either. So the habitable zone is a necessary condition. It's nowhere near sufficient. What a planet actually needs is a stable atmosphere, one that doesn't blow off into space, doesn't lock the planet in a runaway greenhouse effect, and has stayed stable for hundreds of millions of years at minimum. Because complex life doesn't appear quickly. The first evidence of single-celled life on Earth dates to about 3.7 billion years ago. The first multicellular life, the step that matters for anything we'd recognize as an animal, didn't appear until roughly 600 million years ago. That means Earth had to maintain habitable conditions for about 3 billion years, while single-celled life slowly figured out how to cooperate. 3 billion years of stability. That's the real requirement. Not just being in the right zone, staying there with a functional atmosphere, for longer than most stars live through their stable phase. And maintaining that stability requires things that, as far as we know, Earth got almost uniquely right. Most moons in the solar system make sense. Mars has two, Phobos and Deimos, small, lumpy, probably captured asteroids. Jupiter has dozens, most of them small rocks caught by gravity. Saturn's moons are spectacular, but they fit a recognizable pattern. A big planet with a collection of smaller objects in its gravitational territory. Our moon doesn't fit that pattern at all. The moon is enormous relative to Earth. The ratio of Moon to planet mass in our system is roughly 1 to 81. The next largest such ratio in the solar system is Pluto-Charon, at about 1 to 8. And Pluto isn't even classified as a planet anymore. For true planets with large moons, Earth is an outlier. The leading explanation for how the Moon formed, called the giant impact hypothesis, involves a Mars-sized body called Theia colliding with the proto-Earth roughly 4.5 billion years ago. The collision was oblique, not head-on. The impactor was largely absorbed by Earth, and the debris thrown into orbit around Earth gradually coalesced into the Moon. This was not a subtle event. If Theia had been slightly smaller, the Moon might not have formed at all. If the angle had been different, the debris might not have been the right composition. The timing had to be early enough that Earth was still partially molten. Why does this matter for life? Two reasons, and both are important. The first is axial tilt. Earth's axis is tilted at 23.5 degrees relative to its orbital plane, which is what gives us seasons. That tilt is stable. It wobbles only slightly over long periods, about 2.4 degrees over roughly 41,000 years. Mars, by contrast, has an axial tilt that varies between 13 and 40 degrees over millions of years because Mars has no large moon to stabilize it. A 40-degree axial tilt would be catastrophic for any complex surface. Life. The climate swings would be enormous, far larger than anything Earth has experienced. Our Moon acts as a gravitational anchor. Without it, Earth's axial tilt would also wander. How much? Models suggest somewhere between nearly 0 degrees and possibly over 80 degrees. The uncertainty is large, but the range is alarming. The second reason is tidal forcing. The gravitational interaction between Earth and the Moon generates tides. Tides drive ocean circulation. Ocean circulation regulates global temperature distribution. And here's the part that's easy to miss. Tidal forcing early in Earth's history may have played a role in mixing the prebiotic ocean chemistry that eventually produced life. There's an argument, and it's a serious one, that the Moon was a necessary ingredient in the origin of life itself. If that's true, then any planet orbiting in a habitable zone also needs a large, improbably formed moon. That's a second filter on top of the first one. In the early solar system, before the planets settled into their current positions, the inner solar system was a shooting gallery. The asteroid belt sits between Mars and Jupiter. It contains hundreds of thousands of objects. Some of them are large enough to have been classified as protoplanets during formation. The reason most of them never became planets is Jupiter. Specifically, Jupiter's gravity constantly destabilized their orbits and prevented them from coalescing. But Jupiter's role as a gravitational shield goes beyond the asteroid belt. For most of the solar system's history, Jupiter has acted as a deflector, catching or ejecting comets and asteroids that would otherwise have bombarded the inner planets on a far more frequent schedule. A 1994 observation made this visible in real time. The comet Shoemaker-Levy 9 broke apart and slammed into Jupiter over 6 days in July of that year. The impact sites on Jupiter were roughly the size of Earth. If that comet had reached Earth instead, the event would have been an extinction-level strike. We didn't get hit. Jupiter did. There's a hypothesis called the rare Earth hypothesis, developed in detail by paleontologist Peter Ward and astronomer Joe Kirschvink, that without a Jupiter-mass planet in roughly Jupiter's orbital location, the inner solar system would experience catastrophic impacts far more frequently than it does. Frequent enough to reset complex life repeatedly. Frequent enough that the 3 billion years of stability required to get from single-celled organisms to animals would be impossible. Here's where it gets more specific. Jupiter is in a particular orbital location, about 5.2 AU from the Sun, where 1 AU is the Earth-Sun distance. If Jupiter were significantly closer, its gravitational influence would actually destabilize Earth's orbit rather than protect it. There are simulations showing that a Jupiter-mass planet at around 2 AU from the Sun would be catastrophic for Earth's orbital stability. Jupiter had to be roughly where it is, not just present, positioned correctly. And there's another factor. Jupiter's eccentricity, how elliptical its orbit is relatively low, about 0.049. A Jupiter with a highly eccentric orbit would create periodic gravitational disturbances that would likely destabilize inner planet orbits. Many of the giant exoplanets we've detected are what astronomers call hot Jupiters, gas giants orbiting very close to their stars, often in days rather than years. They got there by migrating inward from where they formed, and in doing so they swept through and ejected whatever rocky planets were forming in the inner system. A solar system with a hot Jupiter probably doesn't have an Earth. Our Jupiter stayed put. That's not guaranteed. It's a specific outcome of how our solar system's formation played out. This one surprises people. Plate tectonics, the movement of Earth's crustal plates, the cause of earthquakes, volcanoes and mountain ranges, is not just a geological feature. It's a planetary life support system. Here's how it works. Carbon dioxide enters the atmosphere from volcanic activity. Carbon dioxide is a greenhouse gas, which means it traps heat. Too much of it and the planet overheats. Too little and the planet freezes. But CO2 doesn't just stay in the atmosphere forever. It reacts with rainwater to form carbonic acid, which weathers rocks, specifically silicate rocks, and produces carbonate minerals that get washed into the ocean. Marine organisms use those carbonates to build shells. When those organisms die, they sink. Their shells accumulate on the ocean floor. And then those ocean floor sediments get subducted, pulled under the continental crust by plate movement. Deep in the mantle, at extreme pressure and heat, the carbonates break down and release CO2 back into the atmosphere through volcanoes. This cycle, the carbonate-silicate cycle, is a thermostat. If the planet gets warmer, more water evaporates, more rain falls, more CO2 is weathered out of the atmosphere, temperatures drop. If the planet gets cooler, weathering slows, CO2 builds up from volcanoes, temperatures rise. Plate tectonics drives this thermostat. Without it, the thermostat stops working. Venus doesn't have plate tectonics in the same form as Earth. Its heat escapes differently, through episodic resurfacing events that may occur every 300 to 500 million years. In between those events, CO2 builds up. The greenhouse effect accelerates. There's no subduction bringing carbonates back down to be recycled. We think this is part of why Venus is a hell planet. Now here's the thing people don't realize about plate tectonics on Earth. We don't fully understand why Earth has it and Venus doesn't. Size matters. Smaller planets cool faster and their plates become too rigid to move. Earth's size is large enough to retain heat, but not so large that internal pressures become unmanageable. Water also plays a role. It lubricates the plates, makes them more flexible, lowers the melting point of rock at subduction zones. But the exact combination of factors that produces Earth-style plate tectonics is not well understood. There's no guaranteed formula. Other planets of similar size and composition might not develop it. And without it, no long-term climate regulation, no thermostat, no 3 billion years of habitable conditions. Another filter. About 2.4 billion years ago, single-celled organisms called cyanobacteria figured out how to do photosynthesis. Photosynthesis produces oxygen. Before cyanobacteria, Earth's atmosphere had almost no free oxygen. There was nitrogen, methane, CO2, water vapor. But molecular oxygen, O2, was essentially absent from the atmosphere because any oxygen that formed reacted immediately with iron and other minerals. When cyanobacteria started pumping out oxygen, it was catastrophic. For the organisms that existed at the time, most of which were anaerobic, meaning they lived without oxygen, free oxygen was poison. This event, called the Great Oxidation Event, triggered what was probably one of the largest extinction events in Earth's history, wiping out most of the anaerobic life that had dominated for 1 billion years. It also caused the first global glaciation, possibly a snowball Earth event, because oxygen reacted with and destroyed atmospheric methane, which had been keeping the planet warm. The entire planet froze. Eventually, life recovered. The oxygen-tolerant organisms that survived diversified. Oxygen levels slowly rose to something approaching modern levels. And that oxygen is what made complex life possible, because complex multicellular organisms, with their enormous energy demands, can't run on fermentation alone. They need aerobic respiration, which requires O2. The point is this: oxygen in the atmosphere is not an inevitable planetary condition. It's the result of a specific biological accident, a particular type of photosynthesis evolving in a particular organism, that happened to succeed and spread across the planet. If cyanobacteria had never evolved, or if they'd evolved oxygen-free photosynthesis, which is also possible, Earth's atmosphere would look completely different. Complex multicellular life might never have had the energy source it needed. This was not a guaranteed step. It was a contingent event, a specific thing that happened to happen. For the first 3 billion years of life on Earth, complexity basically stalled. Prokaryotes, single cells without a nucleus, dominated. Then, around 2 billion years ago, eukaryotes appeared, cells with a nucleus, capable of much more complex functions. But even after eukaryotes appeared, complexity didn't immediately take off. Then, about 540 million years ago, something extraordinary happened. In a geological blink, maybe 10 to 20 million years, almost all the major animal body plans that exist today appeared in the fossil record. Arthropods, mollusks, worms, echinoderms, the first chordates that would eventually lead to vertebrates. This is the Cambrian explosion, and it's one of the most studied and debated events in paleontology. The cause is still not fully settled. Possibilities include rising oxygen levels finally crossing a threshold that made complex animal metabolism viable. A series of glaciations that repeatedly stressed and reorganized ecosystems. The evolution of eyes, creating for the first time an arms race between predators and prey that drove rapid diversification. A rise in ocean calcium concentrations that made biomineralization, the ability to build shells and skeletons, suddenly possible. It may have been all of these. It may have been a specific combination that wouldn't have worked without every piece. What we know is that multicellular complexity didn't emerge gradually over billions of years. It exploded once. On other planets with water and carbon chemistry, you might get single-celled life fairly readily. The chemistry isn't absurdly difficult. Amino acids have been found in meteorites. The building blocks are common, but the jump from single-cell to multicellular complex life, that step took 3 billion years on Earth, required specific oxygen concentrations, specific ocean chemistry, and something triggering an arms race of complexity. And we don't know how commonly those conditions co-occur. There are serious researchers who think single-celled life is probably common in the universe. And those same researchers think complex multicellular animal-level life might be extraordinarily rare. The Cambrian explosion might not just be an event in Earth's history. It might be the filter, the bottleneck through which almost no world passes. So far, we've been talking about conditions on Earth itself. Step back, way back. Our position within the Milky Way galaxy also matters, and it turns out we're in an unusually good spot. Galaxies are not uniform environments. The center of the Milky Way, the galactic core, is extraordinarily dense with stars. Stars there are closer together. Supernovae happen more frequently. There's intense radiation from the central supermassive black hole, Sagittarius A star, which periodically erupts in bursts of high-energy radiation. The outer edges of the galaxy have the opposite problem. Star density is low. Heavy elements, carbon, oxygen, iron, the stuff that makes rocky planets, were forged in stellar cores and spread through supernovae over billions of years. The outer galaxy had fewer generations of star formation, and so has lower concentrations of these elements. Earth sits in what's been called the galactic habitable zone, far enough from the chaotic center to avoid constant radiation and gravitational disruption, but close enough to the denser inner regions to have access to the heavy elements needed for rocky planet formation. Specifically, we're about 26,000 light-years from the galactic center, roughly halfway out from the core to the edge, in a region with lower than average stellar density, in a relatively calm area between spiral arms rather than within one. Being inside a spiral arm means more frequent supernovae nearby. Each one sends out a shockwave and radiation that could strip a planet's ozone layer, dramatically increasing surface ultraviolet radiation, which is lethal to surface life. Earth orbits in the gaps between the arms, where conditions are quieter. This positioning, like the other factors, wasn't chosen. It's where we happen to form. And the question is, what fraction of stars in the galaxy are in equivalent positions? Estimates suggest somewhere between 5 and 15% of stars in the Milky Way lie in a comparable galactic habitable zone, which still sounds like a lot. But layer it on top of the other filters and the number starts shrinking fast. Our Sun is a G-type main sequence star. Medium size, medium temperature, medium luminosity. About 7% of stars in the Milky Way are G-type. The most common stars, making up about 70% of all stars in the galaxy, are M-type dwarf stars, red dwarfs. Much smaller, much cooler, much dimmer. For years, red dwarfs were considered promising hosts for habitable planets because they're so long-lived. Some will burn for trillions of years, and because habitable zone planets around them are close enough to detect with current telescope technology. But in the last decade, the picture has gotten messier. Red dwarfs are highly active, especially when young. They emit powerful stellar flares, bursts of X-ray and ultraviolet radiation on a regular basis. A planet in the habitable zone of a red dwarf is, by definition, close to the star, and therefore frequently bathed in radiation that would be lethal to complex surface life. Moreover, tidal locking is almost certain for any planet in a red dwarf's habitable zone. The same side of the planet always faces the star. The day side is perpetually lit and hot. The night side is permanently cold and dark. Whether tidal locking is automatically fatal to life is debated. Atmospheric circulation might redistribute heat, but it creates an extreme environment that complex multicellular life on land would struggle with. There's also a timing problem. Red dwarfs are so dim that their habitable zones are very close to the star. During the star's extremely violent youth, which can last hundreds of millions to over 1 billion years, the radiation environment in that close inhabitable zone is probably sterilizing. Earth's early ocean had water because the young sun, while active, was not so extreme at Earth's distance that it stripped the atmosphere completely. The same is not clearly true for a red dwarf's habitable zone planet. G-type stars like our Sun hit a sweet spot. Old enough stellar generations to have produced heavy elements, active enough to drive planetary chemistry, stable enough over billions of years that complex life can develop without being fried. And G-type stars are about 7% of stars. That's already a significant filter applied before you even get to the planet itself. We've now gone through roughly a dozen independent conditions that had to be met for Earth to become what it is. A star in the right type category, in the galactic habitable zone, with a rocky planet in the habitable zone, with liquid water, with plate tectonics, with a large stabilizing moon, with a Jupiter analogue in the right orbital position, with the great oxidation event, with the Cambrian explosion. Each filter independently narrows the pool. But here's the question that should be uncomfortable. If so many conditions are required, and if complex life is genuinely rare, where is the bottleneck? Which filter is the biggest one? Economist and philosopher Robin Hanson formalized this in 1998 as the concept of the Great Filter. The Great Filter is whatever evolutionary or physical step is so unlikely that almost no species in the universe ever passes through it. The terrifying implication of Hanson's argument is this: the filter is either behind us or in front of us. If it's behind us, if the hard step was, say, the origin of the first self-replicating molecule, or the emergence of the eukaryotic cell, then we've already passed through the hardest part. The road ahead might be open. We might be one of the only civilizations in the galaxy, but we'd be one that already cleared the biggest hurdle. If the filter is in front of us, if the hard step is something civilizations tend to fail at after reaching our level of technological development, then the silence of the universe becomes something darker. Fermi's question, "Where is everybody?" might have a grim answer. They got this far and then didn't make it through what comes next. The absence of any detectable extraterrestrial civilization could mean we're early, or it could mean we're approaching something most don't survive. Finding microbial life on Mars would be one of the greatest scientific discoveries in history. It would also be one of the most disturbing. Because if single-celled life arose independently on Mars, in the same solar system, in the same early conditions, it would suggest that the origin of life is not a rare event at all, which would mean the filter is further along. And if the filter is further along and we've seen no complex civilizations anywhere, it suggests the filter is in front of us. This is why some scientists, including Stephen Webb, in his book If the Universe is Teeming with Aliens, Where is Everybody?, lay out 75 possible answers to the Fermi paradox, and none of them are comforting once you think them through completely. There's an objection to all of this that sounds clever, and it's worth taking seriously. It goes like this. Of course, Earth has all these rare conditions. If it didn't, we wouldn't be here to ask the question. You can't be surprised that the world you live in is one where life is possible, because any world where you exist has to be one where life was possible. The selection effect automatically guarantees that any observer will find themselves in a world that permits observers. This is called the anthropic principle, and it's philosophically legitimate, but it doesn't close the question. The anthropic principle tells you that you'll always find yourself somewhere life is possible. It doesn't tell you how many such places exist. It doesn't tell you how probable your world is. It doesn't explain the silence of the universe, because that silence is observable data from outside our own situation. Here's an analogy. Imagine you've been sentenced to death by firing squad, 50 trained marksmen with rifles. They fire. You survive. The anthropic principle says, of course you survived. If you hadn't, you wouldn't be wondering about it. So there's nothing surprising here. But, and this is the crucial part, that's not actually the right response. The right response is, wait, something needs explaining. Either the marksman missed on purpose, or this is a 1 in a quadrillion statistical accident, or I'm misunderstanding something about the situation. The fact that your survival is a prerequisite for your wondering about it does not explain your survival. In the same way, yes, we had to end up somewhere that permitted complex life. But that doesn't explain why such a place exists with these specific conditions. It doesn't resolve the question of how rare such places are, and it doesn't account for why we see no evidence of anyone else. The anthropic principle is real. It's just not as powerful an argument as it sounds. We can't prove a negative. We can't scan every star system in the observable universe. We can't directly inspect 10 to the power of 24 planets for signs of life. That's not possible with any conceivable technology in any reasonable time frame. But we can narrow things down significantly. The James Webb Space Telescope, launched in December 2021, is already changing what we can detect. JWST can analyze the atmospheres of exoplanets by measuring how starlight filters through them during transits. Different molecules absorb different wavelengths of light, leaving distinctive spectral signatures. If we find a planet with oxygen, methane and water vapor simultaneously in its atmosphere, the specific combination that on Earth requires biological activity to maintain, because oxygen and methane react and destroy each other without continuous biological replenishment, that would be an extraordinarily strong biosignature. We haven't found it yet. The TRAPPIST-1 system, 7 rocky planets orbiting a red dwarf 40 light-years away, at least 3 of them in or near the habitable zone, is the highest priority target. JWST has begun characterizing their atmospheres. The results so far are ambiguous and incomplete. TRAPPIST-1b appears to have little to no atmosphere. TRAPPIST-1c has a rocky surface and appears to have a thin atmosphere at best. This is preliminary. We need more time. SETI, the search for extraterrestrial intelligence, continues. The Breakthrough Listen initiative, funded with $100 million by Yuri Milner in 2015, is the most comprehensive SETI effort in history. It's surveying 1 million nearby stars, the full galactic plane, and 100 nearby galaxies across a wide range of radio and optical frequencies. So far, no confirmed signal. In the next 20 to 30 years, our detection technology will improve dramatically. The next generation of extremely large telescopes, the Extremely Large Telescope, currently under construction in Chile, with a primary mirror 39 meters across, will be able to characterize atmospheric chemistry of nearby rocky planets in far more detail than anything we have now. If there's a biosphere on Proxima Centauri b, the closest exoplanet to Earth at 4.2 light-years, we may be able to detect its chemical signature within a generation. If we look at dozens of habitable zone rocky planets and find no biosignatures, that would be statistically meaningful. Not conclusive, but significant. If we look at hundreds and find nothing, the rare Earth hypothesis becomes much harder to dismiss. There's one more scenario that rarely gets talked about. What if the issue isn't that life is rare, but that intelligence is? Single-celled life on Earth appeared relatively quickly, within a few 100 million years of the planet cooling enough to have liquid water. Given that Earth formed 4.5 billion years ago, and the first evidence of life is 3.7 billion years old, that's a fairly fast start. Some researchers, including astrobiologist David Grinspoon and others, argue this suggests the chemistry of life, once the right conditions are in place, may not be especially improbable. Amino acids, nucleotides, lipid membranes, these form readily under the right conditions. Laboratory experiments since the Miller-Urey experiment in 1953 have repeatedly produced the organic building blocks of life from simple ingredients. If that's true, then life, microbial, simple, single-celled life, might genuinely be common in the universe. But intelligence, language, technology, civilization, that's a completely different question. On Earth, complex nervous systems have evolved independently multiple times. Vertebrates, octopuses, even certain insects show surprising cognitive complexity. Evolution seems to push towards sensory processing and behavioral flexibility given enough time and the right selective pressures. But only one species in 3.8 billion years of life on Earth ever built a radio telescope. That's suggestive. Intelligence and technological civilization might require not just the right planet, not just complex life, not just large brains, but a specific ecological situation that creates an evolutionary pressure for recursive thought, language and tool use. Humans evolved on the African savanna during a period of dramatic climate fluctuation, roughly 2.5 million to 10,000 years ago. The climate swung between wet and dry phases repeatedly, which may have driven rapid encephalization, brain growth, as an adaptation to rapidly changing environments. If a species requires that specific kind of ecological pressure, a highly variable environment that punishes behavioral rigidity, then technological intelligence might be rarer even than complex multicellular life. You could have a planet covered in oceans with billions of years of microbial life. You could have coral reef equivalent ecosystems of complex animals, and still never produce a species that asks, what is this universe made of? If the rare Earth hypothesis is correct, if Earth is genuinely one of the very few places in the universe with complex life, that changes everything about how we should think about what we're doing here. Not in a religious sense, in a very practical, non-abstract sense. If complex life is common, then the extinction of any given civilization is a local tragedy. Terrible, but the universe moves on, replete with other experiments. Earth burning up doesn't matter cosmically. If complex life is genuinely rare, if we are essentially the only instance within our observable reach, then what happens here matters in a way that is hard to overstate. Every species we drive to extinction might be one of the most complex biological structures in this corner of the universe. Every ecosystem we collapse might be irreplaceable, not just locally, but cosmically. The stakes change. Carl Sagan said something precise and worth staying with. If we are alone in the universe, it sure seems like an awful waste of space. That's the intuitive reaction. The universe is vast. Surely it can't all be for one pale blue dot. But the universe doesn't optimize. It doesn't have intentions. It throws conditions at random and sees what sticks. The fact that most of it is empty, cold and sterile doesn't make what exists here less real or less significant. The astronomer Caleb Scharf, in his work on astrobiology, has made the point that the universe doesn't require life to be common for life to be important. A single instance of something extraordinary is still extraordinary. There's also this. If we are rare, we might be early. The universe is 13.8 billion years old. Most of the stars that will ever exist haven't formed yet. The bulk of stellar history is in front of us, not behind us. Low-mass red dwarf stars will burn for trillions of years, providing energy for planets long after our sun has died. If complex life requires billions of years of stellar stability plus the right conditions, and if the universe is still in relatively early phases of its stellar history, then we might not be alone in a cosmic sense. We might just be the first ones here. Early arrivals in a universe that hasn't reached its peak of biological possibility yet, which is a strange thought. That 13.8 billion years into a story, we might still be near the beginning. There's a question that runs underneath all of this, and it's the hardest one. What is life doing in the universe? Not in a teleological sense, not what is the purpose of life as a spiritual question, but in a physical, informational sense. Life is the universe's only known process for generating increasing complexity against entropy. Everything else, every star, every planet, every galaxy, is moving toward equilibrium. Cooling, diffusing, spreading out. Life runs the other direction. It takes energy from the environment and uses it to build more complex structures. It stores information. It replicates information. It occasionally modifies information in ways that allow new structures to survive better. And it's done this on Earth for 3.8 billion years. producing at the end of that run beings capable of reading the genome, understanding nuclear physics, launching telescopes into space, and asking whether they're alone. That capacity to model the universe from inside the universe is genuinely strange. Physicist Lee Smolin has argued that the universe appears fine-tuned for the existence of stars, which are the prerequisite for complex chemistry and ultimately life. The fundamental constants, the strength of gravity, the ratio of electromagnetic force to the strong nuclear force, the mass of the electron, the cosmological constant, are in a range that, if they were significantly different in most directions, the universe would contain nothing but hydrogen, or would have collapsed back on itself before stars could form, or would have expanded so fast that matter never clumped. We don't know if this is selection effect. We're in a universe compatible with our existence by definition, or whether it reflects something deeper about the relationship between physical law and complexity. What we do know is this. In 13.8 billion years, in a universe of 2 trillion galaxies, we have found exactly one place where something complex enough to ask questions exists. One data point, and every framework we have for interpreting that data point, optimistic or disturbing, is a framework we built ourselves. The honest version of this story ends in a place that science doesn't always let itself stay: genuine uncertainty. We might find biosignatures in an exoplanet atmosphere in the next 30 years. We might detect a signal from Breakthrough Listen. We might send probes to Europa or Enceladus, the ocean moons of Jupiter and Saturn, and find microbial life under the ice. Any of these would change the question dramatically. Or we might find nothing. And finding nothing for decades with increasingly sensitive instruments would itself be data. The silence wouldn't be proof of uniqueness, but it would push the probability estimates in one direction. The Fermi paradox is almost 75 years old now. We haven't solved it. We've accumulated more reasons why it's hard to solve. The more precisely we understand what it takes to build a habitable world, the more we realize we can't easily generalize from our own case. What we can do is this. We can keep looking. We can build bigger telescopes. We can send probes to ocean worlds in our own solar system. We can listen harder and on more frequencies. We can continue mapping the distribution of planetary systems and comparing their conditions to ours. And we can hold two things at once: the possibility that we're one of billions of experiments that worked, and the possibility that we're the only one in this corner of reality that ever got this far. Both of these possibilities are serious. Both of them are supported by things we know. And sitting with both of them, genuinely sitting with them, not collapsing too quickly into the comforting version, is one of the more honest things we can do with a brain that apparently evolved for something much smaller than this question. The universe has had 13.8 billion years to produce something that could look back at it. As far as we can tell, it produced us. Make of that what you will.